Well, regarding these structures, what we could do is we could just draw a series of potential structures. So for the first one is with no expanded octet. Now this one's going to have covalent and ionic bonding interaction, and this one, which is going to have an expanded octet. And so what we have here is we have something from this, where we have, let's say, 0% d orbital participation to like 100% d orbital participation. And for this one, we have a kind of a special pi bond here, so the PD. So if this is a 3p orbital here, then we could see how we could have a PD overlap here of the two lobes. And so that would be here. We'd have the p orbital like this. This would be a p orbital by top view. Then yesterday I tried to draw the d orbital by top view, the two lobes coming out, and then try to do a side view as well, like this. This would be the side view. Here. Now, the actual structure, when we think about this, is when we come up with these structures where we don't, what we can have is, it doesn't have to be this one or this one, but what we can do is we could get a hybrid, that is some structure between the two, which is going to have a certain percent d orbital participation. And so as far as things spread out, and so what could this mean, excuse me, what this means is that we could have something from sp3 hybridization alone to sp3 with a d dp pi bond in there. And so the actual structure is probably something between, something, not, you know, a 50-50 mix. Actual structure is somewhere between. Depending on how much d orbital participation we have in distributing the electron density. And so, in other words, some of the electron density can be pushed back here. And so there have been studies about bond length. But bond length, you know, when we look at it, the bond length could be similar because, you know, this is a single bond. Right? This is a double bond. Double bonds are shorter, but this is a single bond with an additional bond. What is the additional bond on this one? This is a sp3 sigma bond, but there's another bond in there. And what is the other bond in there? This is a sp2 sigma with a pd pi. This is a double bond. But this looks like it's just one bond, an sp3 sigma, but do you recognize the other bond in there? Ionic. And having that ionic bond will shorten it as well. And so this bond is going to be shorter than a typical single bond because of the ionic contribution in there. And so it's hard to tell by bond length alone which one it is, because the ionic, in a way, is a double bond as well, because we got this sigma covalent bond plus the ionic bond, so it's two bonding interactions. But probably the actual structure is somewhere between and not halfway, most likely. So it's going to be biased towards one way or the other. Okay, now if we go to H2SO3, it's the same kind of situation. Not H2SO3, H2SO4, the same type of situation. So here we have the structure with just an octet. So we're going to have some covalent ionic bonding here. And then we can expand the octet. So another potential structure here, I'll draw it across since not enough room. But we can form one PD pi bond. We form one PD pi bond, it's going to look like this. We'll leave the other bond like this. So I just dropped the formal charge now to plus and minus. And so same type of situation here. You know, we have an sp3, and so therefore no more p orbitals, so we'll have to use d orbital on sulfur and a p orbital on oxygen on that bond here. And so we got one there. And that should be okay. Now, we still have formal charge there. And so we could draw one more structure for this one. So the one more structure would be to expand the octet further and get rid of the formal charge entirely. So now we have 0 formal charge. What we have here is 2 PD pi bonds. Now, this is tetrahedral, so what is the angle there? This is something I said yesterday. The angle between, so we have, let's say we have one PD pi bond here. The other PD pi bond should be at what angle relative to the first one? Well, it should be at the tetrahedral angle. The tetrahedral angle is 109.5, but when you look at the d orbitals, all the d orbitals are at what angle? 90. Can you see it without me bringing up the slide? Yeah. So they're all orthogonal. So this is the x, xy plane, or xz, yz plane. They're all like this. And so if we have 2 of these at a 90-degree angle, that's going to be quite strange. Are we going to get good orbital overlap? No, not at that angle. You know. And so what that means is, yeah, this one is looking more difficult to expand here. And so what we have is we have 3 structures. Now these 3 structures, probably the actual structure, what do you think? The actual structure will be a mix, right? If there's absolutely 0% d orbital participation, then it should be this. You know, because here we don't need any d orbital participation. But if there's some percentage of d orbital participation in there, then the actual structure is going to depend on how much d orbital participation there is, because over here we're going to have one d orbital participating in the bonding, that is this PD pi bond, and over here we'll have 2 d orbitals participating. So the percent d orbital participation goes up. And so the actual is somewhere between, you know, some in this range. Do you see that? With the extremes here. So actual is somewhere in this range. And so we don't have to have exact percentages. For example, SP would be 50% S, 50% P, but we could have things like 58% S, you know, character, something else, P character, depending on the angles. And so that's what we end up here. So any questions about this? All right, this is the structure. The structure is kind of complicated because of what do we do? Do we expand it? You know, on the one hand, the way I learned it is we expand the octet. We expand the octet and get rid of the formal charge. So this would be the correct structure here, and this is why this structure is shown all the time. When you look at sulfuric acid in the structure, you see 2 double bonds. However, due to the recent quantum mechanical calculations, you know, it's looking like there's a greater percent ionic character in that bond and less D participation, d orbital participation. Does that make sense? So this is advanced topic. Yeah. Advanced topic because, you know, how much the d orbitals participate is still being ironed out. Well, this is valence bond theory anyway. And so what does that mean for this? You know, when we hybridize the d orbitals, are these hybridized d orbitals or unhybridized d orbitals? Is this non-hybridized or hybridized? You know, unhybridized d orbital. This is an unhybridized p orbital. And so that's what participates in the pi bonding here. Well, what happens when we hybridize? For example, PCl5. You know, when we draw out PCl5, we're going to get a structure like this. Trigonal bipyramidal. In this case, the d orbitals hybridize, and we get sp3d hybridization. sp3d hybrids. And so let me just draw this out for you guys. I was going to have you do this one. Is this one of the ones I made on the list? And so what percentage d character is in this orbital? How many orbitals total in that hybrid? 5. Out of that 5, one out of the 5, this is 20% D character in here. This is 20% D. Oops, it's blue. So we draw the phosphorus here. This is the sp3d. 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 One coming out and one going in. And then these all have, how many electrons does phosphorus have? How many electrons? 5 in this particular structure. So here we maximize bonding. We can form 5 bonds if we do this. So, and then we want to minimize repulsions. Maximize bonding, minimize repulsions, because normally sulfur is like this. You know, normally, I mean, not sulfur, phosphorus is like this. Normally phosphorus should form 3 bonds in one lone pair. But if we promote this, you know, this is the 3s, this is the 3p. If we promote this 3s to the 3d up here, then we can form 5 bonds. And then we minimize the repulsions. We minimize the repulsions by spreading out the orbitals, those 5 orbitals, as far apart as possible, which would be sp3d. And then we are capable of forming 5 single bonds like this. And then the chlorines are going to come in. What's the hybridization on the chlorine? sp3. So the chlorines come in here. sp3. You know, 1 in the plane, 2 in the plane, 1 coming out, 1 going in. So it forms like this, 3 lone pairs and 1 single electron. And then I got 5 chlorines come in. 1, 2, 3, 4, 5. Right, and so altogether I'm going to get an expanded octet. Another chlorine is going to come in here. There's going to be more orbitals. Another chlorine's here. I'll just draw this. 3 lone pairs. And 1 chlorine in the back here. All right, so if we look at phosphorus, have the chlorine sp3s come in here and bond here, etc. But again, recent quantum mechanical calculations show that the percent D character is less than this. If the percent D character is less than this, that means we probably don't get this kind of full hybridization. So at the other extreme is we'll look at 0% D. If we go to 0% D, what's that going to look like? If there's no D orbitals participate in this, then the max we can have is an octet. Okay, and so what's going to happen is phosphorus is going to have a maximum of 4 bonds. 1, 2, 3. Say 4 bonds. And then there's going to be that would complete its octet. But what about the 5th chlorine? Well, the 5th chlorine is going to be ionic. And so if phosphorus only has 4 bonds, that gives it a positive formal charge, and chloride is going to have a negative charge on that, formal charge or oxidation state. And so this 5th bond is actually ionic. Yeah. Well, this comes to this. We're going to have these weird resonance forms. These weird resonance forms is where the ionic bond is. So right now I have the ionic bond in this equatorial position going back. But I can move that ionic bond to different positions. So for example, I'll put the ionic bond in the axial position at the top here. So this is negative, phosphorus is positive, and that means the chlorines are all going to be bonded like this. You know what, I'm not going to draw the lone pairs on the chlorine to save time, but you should always draw the lone pairs here. How many of these can I draw? 5. And so what's going to happen is I don't have 4 covalent and 1 ionic. Do you know what the hybrid's going to look like? The hybrid, all the bonds are going to be equal in terms of ionic character. In fact, all the this is going to be what we call 20% ionic, all bonds. And so the hybrid is going to have a charge like this. You know, we're going to have these 5 chlorines here like this. And these bonds are going to be 20% ionic, 20% covalent. Each chlorine is going to have a charge of what? -1/5, basically, if we spread out the charge across all of them. It's taking -1 dividing by 5. And the phosphorus is still going to be plus. Does that make sense? This way we don't have to have any d orbital participation. And so we're going from 0% d orbital to 20% d orbital. But the reality is it's probably somewhere in between. We'll probably have a little bit of d orbital mixing in there to form the hybrids. Okay, but not full 20%. If we go to SF6, it's the same thing. You know, if we don't want to expand the octet, then we're going to maintain an octet that is 4 bonds max. The SF6 is 6 fluorines, and so 2 of those fluorines will be ionically bonded. And of course, we can draw resonance forms for that. This. And then the actual structure is going to be a hybrid in which all the bonds are equal. There's just a higher percent ionic character. And this way we avoid having to do any d orbital hybridization in there. And the reason we want to avoid the d orbital hybridization is because of this. The whole idea of expanded octet like this would be sp3d2. And so 2 out of the 6 orbitals would be d, which would be 33 1/3% d character. But they say expanded octet is questionable since wave function calculations show very little contribution from d orbitals. And so the percent d is probably not 33%. The percent d is quite a bit smaller, and the percent ionic is much greater. Here we can see electron density. Where do these electron density maps come from? Well, you know what? And this, look at if you look, this is the electrostatic potential map. This is sulfuric acid on the left. These are different ways of representing. This is called a ball and stick. These are contour maps here showing surfaces, and this is showing the surfaces as well. This is the sulfate ion here, showing the same thing, surfaces with the sulfate ion. Now, all this complication comes from the fact that valence bond theory is not a full, rigorous quantum mechanical approach to molecules. What is a full, rigorous quantum mechanical approach? In other words, we don't have, all this stuff I've been talking about, we don't have to worry about if we just use another theory. What's the other theory we can use? What's the other theory we could use to, all this is because of the limitations of valence bond theory, all this dehybridization. Although hybridization appears here as well in this theory, but the way we visualize bonds occurring is quite a bit different in this theory. The theory name is molecular orbital theory. Do you recall that there are two theories for bonding? What's the difference between the two theories? You have that memorized yet or not? Somebody tell me the difference between the two theories for bonding. I know people are busy. So. No. I know people are busy, but skimming through your notes, and then picking it up little by little every day is a bigger time saver than you might think, versus cramming it the night before the test. It's a lot bigger time saver because it doesn't take very long to read through your notes and then just make a note of it. And however you take your notes, you might annotate the book, you might do whatever. But there are two theories in bonding. This is, I don't know how many times I've repeated this, a lot. But I know repetition, me coming up here and saying it isn't as effective. Yeah, and what's the difference between valence and molecular orbital? If somebody asks you what's the difference, would you just spit out verbatim what I said about it, or would you come up with your own words? You come up with your own words. Because what I say about it isn't so meaningful. Not as meaningful as what you say about it.
Like overlapping versus.
Yeah, there are two different ways of describing a bond, but essentially what's the difference? Why do we have two different ways? Why not just one way? Somebody asks you why. Why do you have two theories? It's dumb to have two theories. Just have one theory. What, one theory is a backup, or you flip the coin? What do you do? Which theory do you use to describe a bond? Having two theories is dumb. You want two theories for the atom? Or is it dumb? Point was, it wasn't dumb at all. And so somebody explained to me why it wasn't such a bad idea to have two theories for the same thing. A bond. Yeah, a molecule.
They're close enough.
I'm sorry?
They're close enough, even though the valence bond theory is a lot easier.
Well, it's not that they're close enough. Sometimes they're very far apart. For oxygen, they're very far apart. But they're close enough so that you can make a sacrifice. You should probably not say they're close enough, because if they're close enough, just use one, not the other. You have to give me an argument why we have two rather than one. And so if they're close enough, I'll just pick one. Flip the coin and pick one. But what you said, the second part of what you said is important. That's the key. What was the second part you said?
Valence bond theory is just easier.
Yeah, valence bond theory is easier. So why don't we just use valence bond theory and give up molecular orbital theory? Valence bond theory.
It's not a
Yeah, it's not exact. Right. And so these are limitations you deal with, but we wouldn't deal with that with molecular orbital theory, because molecular orbital theory, we don't have to do that. I mean, the d orbital participation came from molecular orbital theory, you know, how much d orbitals are mixed in there. Well, what is molecular orbital theory? Molecular orbital theory is this. You know, atomic orbitals are isolated on atoms. Molecular orbitals span 2 or more atoms. So we learn a new set of orbitals. This new set of orbitals encompasses the entire molecule. And calculated orbitals for fluorine. Analysis of the total wave function describing F2 in its lowest energy states. MOs are distributive linear combination. This is just random here. But ignore this. What do we do? These are the molecular orbitals for fluorine here. And so the molecular orbitals start off like this. Kind of ignore the shape. This is sigma 2s. This is sigma 1s. Sigma 1s should look like the cigar, not like this. The sigma star 1s is like this. It has a node. All the starred orbitals have nodes. So this is sigma 2s. This is 2 fluorine atoms bonded together by a single bond. Sigma star 2s, and then we have the sigma 2p, and then et cetera, et cetera. And so you learn these orbitals. These are the orbitals for fluorine. What happened to the 1s? What happened to the 2s? What happened to the 2p? The 1s, the 2s, and the 2p aren't there anymore. Basically, what happens is this. You do something called a linear combination of atomic orbitals. And so the molecular orbital is we take an atomic orbital from atom 1 and an atomic orbital from atom 2, and we do a linear combination. This linear combination means we do this plus minus. And so what we end up with is what we call a bonding orbital and an anti-bonding orbital. And so a linear combination of 2 atomic orbitals produces 2 molecular orbitals, a bonding and an anti-bonding. And so let's just read the points. Each MO can be represented mathematically as a linear combination of AOs. We call this LCAO. That's an important acronym. The total number of MOs is equal to the total number of AOs. AOs, atomic orbitals, MOs, molecular orbitals. MOs can be classified as bonding, anti-bonding, and non-bonding. Non-bonding is when they don't mix. They're just left alone. And that happens. They don't mix and they're left alone, and they just stay as, essentially as atomic orbitals. The electron configuration for the molecule is obtained by placing electrons into MOs. So we fill the MOs. In other words, that last statement is we fill the MOs just like AOs. And so what happens to the AOs? If we look at hydrogen, we have one s orbital on one hydrogen and one s orbital on another hydrogen. When we do an LCAO, we generate 2 molecular orbitals. The first molecular orbital is shown here. This is one single orbital. And so we see hydrogen A, hydrogen B here, and this orbital encompasses the entire molecule. Now this orbital can only hold 2 electrons max. And so that's bonding, where we get constructive, mixing, and then we have anti-bonding, where we get destructive. In other words, one will be phase up, the other phase down. In other words, a positive amplitude, negative amplitude. And they don't mix. When they don't mix like this, we get a nodal region here. Now the reason this is called a bonding orbital is because when we look at the probability density function for this MO, we see good probability of the electron density between the 2 nuclei here, which is going to hold the positive nuclei together. If we look at the anti-bonding MO, which is on the top there, you see very little, in fact 0 probability of finding the electron in the middle there. And in other words, the 2 nuclei are going to see each other and they're going to repel each other, and so those are called anti-bonding here. In terms of energies, the bonding MO is much more stable than the anti-bonding. The bonding MO is going to be stable, more stable than the individual atomic orbitals, because forming bonds releases energy, breaking bonds constantly. And so what we get is we got an energy level diagram, but this energy level diagram shows both atomic orbitals, atomic orbital 1s on atom A and 1s on atom B, and the molecular orbitals, the sigma 1s and the sigma star 1s. The sigma comes from this. Sigma MOs, this is different than sigma valence bonds. Sigma MOs will have electron density within the internuclear axis, like this. And so these would be sigma MOs, because the electron density is within the internuclear axis. Now, we're going to go to, well, actually, let's use this first. Bond order. Bond order is what makes a bond. What makes a bond is having more electron density in the bonding MO versus the anti-bonding MO. So if we put 2 electrons here, then we're going to form a nice bond here. If we put 2 electrons here and 2 electrons here, then the bond cancels out because the anti-bonding cancels out the bonding and we get no bond. If we put 1 electron here, we'll still have bonding, you know. And so that gives us bond order. The bond order is how many electrons we have in the bonding versus how many we have in the anti-bonding. 2 electrons make a bond. That's the reason we divide by 2. We'll do some calculations here. So if we look at hydrogen, what is the bond order of hydrogen? So this is the hydrogen here, H2. And so we'll take 1 hydrogen, 1 hydrogen. So H2 will have 2 total valence electrons, 1 from each hydrogen. And so we fill it. An MO can hold a total of 2 electrons. We have it here. And so if we have 2 electrons in the bonding, we call it a single bond, and the bond order is 1. And so the bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2. So that gives us a bond order of 1 here. Now, what happens if we knock an electron off? If we knock an electron off hydrogen, the molecule will form H2 plus, this diatomic cation here with a positive charge. And it turns out that is still a reasonable stable species because there's an electron in the bonding orbital. If there's an electron in the bonding, there's some bonding interaction. In other words, the bond order here for the H2 plus ion is 1 bonding minus 0 antibonding divided by 2. It has a bond order of 1/2. So this is a 1/2 bond here. Now, if we go to HE2, each helium has 2 valence electrons, so we have 2 of them, so it gives us a total of 4 valence electrons for HE2. We have 2 of those in the bonding, 2 of those in the anti-bonding. So the bond order for HE2 is shown here. 2 electrons in the bonding minus 2 electrons in the anti-bonding gives us a bond order of 0. So the anti-bonding electrons cancel out the bonding electrons here. However, the He2 plus, if we knock an electron off one of the heliums and we end up with 3 electrons total, then this actually exists. He2 with a positive charge will have a bond order of 1/2 because we have 2 electrons in the bonding, 1 electron in anti-bonding, which gives us a bond order of 1/2. So He2 plus exists, He2 does not. And so MO theory can predict things like this as well, whereas valence bonds wouldn't have predicted He2 plus to exist. All right, we're going to move on to the second period elements. The first period uses only the 1s, so when we get into the second period, we get the 2s and 2p orbitals. And so when we do this, we have to, this is p orbital overlap. This is for valence bond theory. For MO theory, we're going to have pi MOs as well as sigma MOs, and we can see how that happens here. So let's take a look at how we can do linear combinations of these. So let's do a linear combination of these. These are PZ here. Normally we call these PXs, but they oriented differently, the Z-axis like this. So we have a PZ, PZ. Do you see the positive, positive? That's going to result in constructive. And when we look at the electron densities in the internuclear axis we call a sigma. And since this is coming from 2pz, we call it sigma 2pz. All right, we also have to do this. When we do linear combination, we're going to do the positive with negative amplitude. That's going to lead to destructive. This is called an antibonding. This would be the sigma star 2pz with a node right in the center here. You can see the major lobes are on the opposite ends here. Unfortunately, you're going to have to learn how to draw these as well and name them. So you'll have to memorize these orbitals too. Now, there is the px and the py. And so the px, they have sticking straight out of the board. And this px is sticking straight out. And so what they have is they have these 2 px's like this. I should have brought the p's. And another one here. And when we do linear combination, we're going to do positive amplitude, negative amplitude, we get constructive. So we end up with one big lobe projecting out, one big lobe projecting in. The 2 nuclei are here. This is, although it's hard to see, this is called a pi. It's called a pi because it would have been easier if we looked at this one, the py's. If we look at the PYs here, you can see how they are going to add blue, blue, red, red. You get a big blue here, a big red here. This is pi because when we look at the internuclear axis, which is shown as a black line here, is there any electron density? No. And so that's why we call it pi. The electron density is above and below the internuclear axis. This is one single orbital. This one single orbital, which looks like a gigantic p orbital, can hold a max of 2 electrons. Now, if we do the red-blue, we're going to get destructive, and so this leads to the antibonding pi star 2py. And you can see the 4 lobes are essentially repelling each other, and there's a node here. If we take this orbital and just rotate it 90 degrees this way, and this orbital rotate it 90 degrees this way, then we get these two here. Do you see? These two are just these rotated 90. So we're going to generate the diagram here. So we generate the diagram here. Here we have the P's. When we look at this, when we do the P's, actually let's redo the whole diagram over here. These orbitals aren't as hard as you might think to memorize. And so what we got here is we got the, we're just going to look at the valence. Second period valence. What's shown here is the core as well. We're going to ignore the core and just look at the valence. So these two in the bottom we'll ignore. So we got the 2s on atom A. We got the 2 p's on atom B. Excuse me, on atom A. We got the 2s on atom B and the 2 p's on atom B. Yes. And so when we generate the MO diagram, we bring these together to bond. And so we do an LCAO. We do an LCAO. So these are the AOs here. This is the AO. This is going to be the MO. This is going to be called an MO diagram, which is just the energy level diagram. And so the 2s can add in 2 ways. We're going to form a bonding. This is going to be the sigma 2s. The sigma 2s is going to look like this. Atom A, atom B, it's a cigar shape. So it looks like this. Just in the plane. Then they're going to add destructively, positive and negative amplitude, and what's going to happen there is we have the 2 nuclei here, and they just repel each other. So that's what I'm trying to show here. We've got this cigar shape here, atom A, atom B, and then they add destructively, constructive and destructive. Well, obviously constructive is going to be more stable. And then there's a nodal plane here in the middle. So this is a nodal plane. Now the P's are going to add differently. Now the sigma is more stable. And so the sigma is end to end, like this. And so let's just do it like this. We'll take one like this and one like this, end to end. And so if I look at that, that's going to produce something like this. Or actually, let me draw it more accurately. Basically, these 2 lobes add up here, make this big lobe here. And these lobes in the back shrink. Here. So that's what I'm looking at here. I'm getting rid of the color coding. But essentially it's like this. These 2 lobes that come at each other will grow. Those will shrink. Now, we've got the bonding and then we got an antibonding. The antibonding is these 2 lobes are going to shrink. And so the antibonding is going to look like this. These lobes shrink here and these lobes grow in the back here. And then we got a nodal plane here. And so this would be sigma 2p. This would be sigma star 2p. And then let's go with the p's like this. If we do the p's like this, then those are going to form pi. And the pi's are going to be weaker in terms of bonding interaction. So we got the lobes adding, or we reverse it. If we reverse it, then we'll get the pi antibonding. So antibonding will be here. Actually, I should even it up. Antibonding's here. Now the antibonding is going to look like this, where the four lobes kind of stay far apart as possible. Not that node. And so we call this a pi 2p here. And this is a pi star 2p. So which orbital am I looking? I'm looking at this. Here's my pi 2p. You can see the nodal plane right there. And then let's go up. Oops. Go up a little bit. This one is this one here. I don't know why they did that. This one should be over on top of there. This is the pi star 2p here for this one. This is the pi 2p, this is the pi star 2p here. So we got that. So the bonding and the antibonding. Well, the only difference between the other set, this set, and this set is they're tilted at a 90-degree angle. And so we're looking at this orbital next, the one coming out and one going in. One coming out, one going in. And so that's going to be exactly the same energy. The only difference is we have one lobe coming out of the plane and one lobe going in. Plane like this. And then we're going to get a pi star. Pi star is one lobe coming out here, one lobe going in here, one lobe going in here. And then there's going to be a node right in the center here. I should do the node in a different color. So all the antibonding orbitals will have a node. And so the MO diagram is going to look like this. If we get rid of all the orbitals, then it will look like this. What we're looking at is the top diagram here. This is the MO diagram. So sigma 2s down there, sigma star 2s to sigma 2p, and then we have the 2 pi 2p's, followed by the 2 pi star 2p's, followed by the sigma star 2p. The energies are balanced like this. See it there. As the bonding orbitals will be the opposite of the antibonding orbitals in terms of energy. All right, so that's normal. This is abnormal. This diagram is abnormal. Can you see what's different about this one? Which orbital is out of place? Yeah, the sigma is out of place, sigma 2bz. And so this is what we call the normal diagram. This is going to be z, a higher z greater than or equal to 8. And then we have this one, the abnormal diagram. Abnormal diagram, the sigma 2p got bumped up. So in the abnormal diagram, we have this. We have the sigma 2s in its normal place, the sigma star 2s, and we expect to see the sigma 2p, but the sigma 2p got kicked up here. And so now the sigma 2p is way up here above the pi 2p's. So here's the pi 2p, and then we have the pi star two p's, and the pi star 2p, and then the sigma star 2p. This is for Z less than or equal to 7. Z is the atomic number of the atoms, A and B. So why is that? Why that is this. Take a look at the sigma 2s versus sigma 2p. Look at these two orbitals. These are two bonding orbitals. But if you look at the volume of space, do you see? If you take this one and bring it up there, they kind of overlap. In fact, they're occupying the same volume of space. Do you see that? And so what we have here is we have the reason that the sigma 2p gets kicked up like this is because of repulsions with the sigma 2s. The sigma 2p electrons are in the same volume as the sigma 2s, so you know they've got too much electron density in the same volume. We're going to get electron-electron repulsions. Why doesn't it happen here? Why it doesn't happen here is because the higher the Z, the more the orbitals get pulled in. Which orbitals do you think are more penetrating? A 2s or 2p? Which orbital is more penetrating? A 2s or a 2p? 2s is more penetrating. And so what happens here is that they can avoid each other. Repulsions aren't so great. And so this is why I call it the normal. Repulsion is minimal. The reason it's minimal is because the sigma 2s is more penetrating, so the sigma 2s gets pulled in closer. And then the sigma 2p is less penetrating. So if I look at the sigma 2p, you can see that there's some space where they don't overlap. And that means the electrons they have some breathing room. They have their own personal space, right? And so this is like having two bedrooms versus one bedroom, you know, you share with 4 electrons. If you have 2 bedrooms, then some electron density can go out here for 2 of them, right? But over here, if you got 4 electrons sharing the exact same space, that is, these are less penetrating. So if it's less penetrating and Z is bigger, then the orbitals are going to be bigger. And so this would be the sigma 2s. Since Z is higher there, it pulls in the electron cloud. Z is lower here, it doesn't pull in the electron cloud as much. Sigma 2p. And so they can't really avoid each other. They're always occupying the same place. But then again, the orbitals are bigger. But well, this is the explanation given to why. Yes. And so unfortunately, you have to memorize that. Now, what does that mean? That means we have this. That means we have 2 different diagrams. And so now here, Z is less than 7. Z is less than 7 means both orbitals aren't pulled in as much, so we have to use the abnormal one, which is shown here. Do you see the sigma 2p given in green? It's the abnormal position. But we're going to look at different molecules. Li2. Li2 is diamagnetic, all paired electrons, and bond order is 1. This is a molecule. The beryllium Be2 molecule doesn't exist. It would have a bond order of 0 because we have 2 in the bonding, 2 in the antibonding. They cancel each other out. B2 does exist. B2 would have a bond order of 1. It would be paramagnetic. It's got 2 unpaired electrons. The diatomic carbon does exist also. Diatomic carbon would have a double bond. What it has is it has 2, 4, 6 electrons in bonding, 2 electrons in antibonding. And so we got more electron density in the bonding than antibonding. In fact, 4 electrons excess for it. N2 we already know. N2 has a triple bond. That's very common. And the triple bond here is shown here. We got 2, 4, 6, 8 bonding electrons versus 2 antibonding electrons. It gives us a triple bond. It's diamagnetic. All right, now once we hit oxygen, then we use the normal diagram. Do you see this is a normal diagram? Look at the green orbital position. O2 has a total of, actually, each oxygen is 8 electrons, so we've got 16 electrons to fill in here. So we've got 16 electrons. We just fill the orbitals. We use Hund's rule here. You see Hund's rule. But anyway, let's count them. 2, 4, 6, 8 bonding minus 2, 4 antibonding. That gives us 4 divided by 2. It gives us a double bond. And that's what we expect. O2 should have a double bond. But one thing that's different here is O2 is paramagnetic here. In valence bond theory, O2 is diamagnetic. F2, single bond. Ne2 doesn't exist. Bond order is 0, all the orbitals are filled. So it turns out that MO theory is much more powerful because we can get excited states, therefore we can predict the spectroscopy. This is just MO diagram, C2. Here, this is what we call the abnormal. You know, if we try to put C2 in the normal diagram, it doesn't work. Because if we put C2 in the normal, it gives us paramagnetic. But C2 is diamagnetic, so it goes into the abnormal diagram. The sigma 2p is bumped up. So, O2 is paramagnetic. This goes into the normal diagram here. You can see this is liquid oxygen. Look at liquid oxygen is trapped by the magnetic field. And so it's just stuck there in space. And so here the magnetic interaction is stronger than gravitational. O2 is definitely paramagnetic. This comes from MO theory and from experiment. Valence bond theory is wrong because it predicts diamagnetic. Now let's look at heteronuclear. Heteronuclear is the higher the Z, the smaller the orbital and the lower the energy. So that's what this is showing. You know, this is showing that the higher the Z, the lower the energy and the smaller the orbital. That goes for the S. The P's are less penetrating. So those aren't going to be impacted as much as the S's. The S is more penetrating, so they're going to feel that nuclear charge more. That's what this is showing. So when we have heteronuclear, these aren't at the same level. You know, this is homonuclear. This is supposed to be at the same level. I tilted a little bit. But this is homonuclear because these orbitals are the same. Now, what if I did heteronuclear? What if atom A and atom B were different? In this case, they're the same. But let's say, what if atom A and atom B were different? Let's say atom B had a higher Z. If atom B had a higher Z, it pulls these orbitals down lower. And so the MO diagram looks lopsided a little bit. Let's take a look. Do you see here? Here we have carbon. We have oxygen here. You see oxygen is more electronegative. It has a higher Z. It gets pulled down. Now, which one do you use? Because oxygen you use the normal, carbon you use the abnormal. Which one did we use here? Did we use the normal or the abnormal? We use the abnormal. And so it looks like carbon, we use the MO diagram for carbon, not the MO diagram for oxygen. It's weird because normally I would have think that oxygen would have dominated, right? And we'd use the MO diagram for oxygen. But that's what we observe here. Here are the MOs. Except these MOs, take a look at the system here. Do you see these numbers here? The nomenclature system's a little different. You don't have to worry about that. In fact, there are a whole bunch of, as you get more and more into it, there's a whole bunch of symbols that we use for orbitals, way beyond what you guys have seen in this. But they all deal with map, symmetry groups. In benzene, we use valence bond theory, but we could also use MO theory. This is valence bond theory for benzene here. You can see. Here are the sigmas. These are all the sigma bonds. This is the pi bond. Remember, in benzene, we have alternating. So we get pi bonding, delocalized pi bonding here. But in terms of MO theory, we don't have to worry. These are the molecular orbitals for benzene here, and these molecular orbitals span. So this would be bonding MO. Here, this is bonding MO, anti-bonding, anti-bonding, anti-bonding. And so when we do benzene like this, we see that we naturally get delocalized electrons. These two electrons can go anywhere in the upper lobe or the bottom lobe here, and these are delocalized as well. Some, not as much. You can see that the electrons become naturally delocalized in MO theory. But that gets more complicated, of course. This is ozone. Ozone and valence bond, we did that. Normally we pick one. Ozone would have a double bond and a single bond, sp3 and an sp2. But we see that it's totally delocalized. This is the MO for ozone here. These are the MO. This is the MO diagram for ozone. We have extended pi systems like this, where we generate a whole bunch of MOs. So if you take like 10 atomic orbitals, we're going to get 10 molecular orbitals. If you take 100 atomic orbitals, we're going to get 100 molecular orbitals. And so for some of these extended systems, we get so many molecular orbitals, they form what's called a band of molecular orbitals. And the band of molecular orbitals is what's used in band theory, like semiconductors and conductors and insulators. We have bands, band theory. Because when you're looking at a semiconductor like silicon has so many atoms. And like say we have an Avogadro's numbers worth of atoms that we're doing the whatever. We're going to get a huge number of MOs. And so in this kind of band theory, this doesn't apply strictly to band. HOMO and LUMO. HOMO stands for highest occupied molecular orbital. LUMO stands for lowest unoccupied molecular orbital. And there's an energy gap here. That energy gap is typical light. Light will excite this, the HOMO and LUMO. And so what we have when we got these conjugated systems like this is we have brilliant colors. Beta carotene has brilliant color to it. It's due to the jump from HOMO to LUMO in LIGO. All right. Well, anyway, this is what I want you guys to do in addition. MO, we aren't going to get any more complicated than diatomic, and no more complicated than heteronuclear diatomic. And so what I want you to do is this. After you finish, we still have this. I asked you to do SpCl3, right? And some of those others. But after you do those, I want you to do O2. O2, we're going to analyze it two ways. We're going to analyze it using valence bond, and we're going to analyze it using MO. For MO, I want you to draw the orbitals and fill with electrons. And then what we're going to do is we're going to compare the electron density map of MO for O2 versus valence bond, the electron density map for valence bond theory. Okay. Then we're going to compare the properties, bond order and magnetic properties. That's it. All right, so I'm going to stop talking here, and we'll do it.